This is Thermochemistry Part 2. We're looking into heat being released or absorbed during chemical changes. We ended the first part with this exam-style problem, so you've had perhaps some time to try to solve that. So let's look at the solution. Remember, this is enthalpy of products minus enthalpy of reactants all the time. So the products up on the right, the reactants down on the left. Delta H is 300 kilojoules minus 100 kilojoules, or 200 kilojoules. And this is endothermic because we're going from a lower energy to a higher, so it's plus 200 kilojoules. Now, I'm giving you a number of reactions on this page, and you tell me if we've got an exothermic or endothermic process in each line. Here's the complete combustion of propane. Exothermic because delta H is shown as being a negative number. Here is the reaction of hydrogen and iodine, gases. Endothermic because delta H is positive. Now there's a different way to show the delta H as part of a reaction, and here's one of them. This is exothermic because delta H shows up as a product. That must mean that the product energy here is less than the reactant energy. Here's another one. We don't have a number, we just show delta H on the left of the arrow. So this is endothermic. Delta H is shown as a reactant. Now the enthalpy change is an extensive property of matter. Remember, an extensive property is one that changes as the amount of matter changes. That's why we report enthalpy change as the delta H in kilojoules per mole. The more moles of reactant are involved, the higher is the enthalpy of reaction, or the more negative is the enthalpy of reaction if it's negative. Delta H then is an extensive property. So you have to multiply the enthalpy change for 1 mole by the number of moles involved in the reaction. What are the units? The units for delta H are kilojoules per mole. Symbolize mole to the negative 1 power. So here's a question. When 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for a process in which 5.8 grams of methane is burned at constant pressure according to this equation. You'll have to balance the equation. First, this is one you've probably done before. There is the balanced chemical equation. And 5.8 grams, we can see here, is 0.36 moles. 890 kilojoules released per mole, so we multiply by 890 kilojoules per mole, and we get 320 kilojoules. There's 2 significant digits here based on 2 sig digs in the grams of the sample. Also, there's probably just 2 sig digs here on the kilojoules. So why don't you practice one with an endothermic process that you're familiar with. The amount of energy absorbed when 345 grams of sodium hydrogen carbonate reacts with an excess of citric acid. We start with 1 mole of sodium hydrogen carbonate, 84 grams. We can calculate the moles reacting in this manner. 4.11 moles. We have 4.11 moles. We then look to the delta H, and the energy absorbed must be 4.11 moles times the molar enthalpy. 862 kilojoules would be absorbed. Calculating molar heats. First, the freezing point is the temperature at which the solid and liquid of a substance are in equilibrium at 1 atmosphere pressure. The enthalpy of fusion is the amount of heat energy required to melt 1 mole of solid at its melting point. This depends on the attraction between the solid particles that are keeping them in their solid matrix, their crystalline form. For water, of course, the freezing point is 0 degrees Celsius, or 273 Kelvin. And delta H of fusion is 6.02 kilojoules per mole, or 334 joules per gram. In vaporization, the boiling point is the temperature at which all the liquid is turning into gas, where the vapor pressure of the liquid is equal to atmospheric pressure, and therefore liquid and gas are in equilibrium. The enthalpy of vaporization is the amount of heat energy needed to vaporize 1 mole of liquid at its boiling point. It's a measure of the attraction between the particles of a liquid that are keeping them from turning into a vapor. The boiling point of water is 100 degrees Celsius, and the delta H of vaporization is 40.7 kilojoules per mole, or 2260 joules per gram. So how much heat energy is absorbed when 47 grams of ice melts at STP? And we give you the delta H of fusion here. How much heat energy is absorbed when the same mass, 47 grams, boils? And it's instructive to compare the amount of heat energy in steam versus the amount of heat energy in water. Once ice melts, how much heat did it take to melt the ice versus how much heat did it take to boil the water? It's considerably more heat involved in the steam. That leads us to a story. The Battle of St. Charles, Arkansas, most people have never heard of, took place in the summer, close to summer of 1862. And this is the story that was reported in the Philadelphia Inquirer 4 days later. A cannonball entered the boiler of the gunboat Mound City, causing a fearful explosion and loss of life. The crew consisted of 175, of whom 125 were killed and wounded. The rest of the story is interesting. Most of the people on board who died showed absolutely no wounds. The steam boiler had burst, and the steam had filled, live steam, you can't see it, it's a vapor, very, very hot. It filled the compartments, and the people took one breath and were killed just by breathing the steam. So let's do one more thing. What quantity of heat energy is released when 506 grams of liquid water freezes? And what mass of steam is required to release 4.97 times 10 to the 5th kilojoules of heat energy as it condenses to water? And you can use the molar heats that we showed you on a previous slide. Heat capacity is a measure of an object's ability to absorb energy in a 1 degree temperature rise. The unit is in joules per degree Celsius. Specific heat capacity is a measure of a substance's ability to absorb energy per gram in a gram degree temperature rise. So it's how much heat is needed to raise, or how much heat is given off when absorbed when 1 gram changes by 1 degree. This is an intensive property. And we might ask, which has a higher specific heat capacity, oil or water? And really, you might think, how much heat does it take, or if you're given a certain amount of heat, which goes up faster in temperature, 100 grams of oil or 100 grams of water? And I think you'll know, if you've ever cooked anything, that the oil warms up a lot faster than the water. Here are the specific heats and molar heat capacities for some common substances at 25 degrees. So this is in grams and this is in moles. And you can see that water, liquid water, has a higher specific heat and molar heat capacity than anything else on the list. That, by the way, is because of its polar nature and its hydrogen bonding. So you can now practice with these two problems, and if you use the formulas that you have learned, you should be able to answer these questions. Here's a challenge problem. given an amount of aluminum and amount of heat put into it, what is the final temperature of the aluminum? And you can go back to a previous slide to find the specific heat capacity of aluminum. Now there are combination problems that you will see in some tests. During a phase change, the kinetic energy remains constant and only the potential energy changes. If the kinetic energy is constant, the temperature is constant, and the only thing you need to worry about is the heat of fusion or the heat of vaporization and the total amount. There's no temperature change, so that doesn't crank into the problem. Please note I have another set of slides and another YouTube video that specifically talks about those calculations. During phase changes then, you'll use the enthalpy of fusion or vaporization, and if you have a temperature change, you're going to be using the specific heat capacity of the substance. So here's the heating curve of water, and here are the various formulas you will use. Here, when temperatures are changing, you use the specific heat capacity. Here, when you're heating up liquids, and here when you're heating up gases. And then for melting, you use the delta H of fusion times the mass or the number of moles. And here, when you're vaporizing, use the molar heat or gram heat of vaporization times the moles or mass for any time you're boiling off something. So here's another practice problem. Energy needed to convert 22 gram sample of ice at minus 12 degrees to steam at 210 degrees. This will require 5 calculations. I'll show you those graphs on the previous page, and you can look up the molar enthalpy change and the specific heat capacities. There's your graph and your formulas. Finally, calorimetry is the science of measuring heat based on observing temperature changes when something absorbs or discharges energy as heat. Ordinarily, we use constant pressure calorimetry, so we don't have to have such expensive equipment. This you'll use a coffee cup calorimeter to work with. Bomb calorimetry, however, is used at places like Southwest Research to measure the amount of energy in, say, fuels or food. And it requires a rather expensive apparatus in which to conduct the experiment. This is a coffee cup calorimeter, or this is a more expensive one, may not even be as good. Here you can just stir with a straw, and here you're stirring with something a little more mechanical. This is a bomb calorimeter. The fuel is being mixed with an oxidizer like oxygen or sodium peroxide, and you can see the temperature of the surroundings is monitored with a thermometer here. You do not measure the temperature change in here because in most cases it would destroy the probe or the thermometer. Here all you have running in and out are ignition wires so that you can get the reaction started. Here are some thermochemical properties of certain fuels. You see they are very, very different in their amount and caloric value in food. Now we're working with calories. Calorie is larger than a joule. Calorie is 4.134 joules. And a large calorie or a kilocalorie would be 4.134 kilojoules. Your next lab would be a lab to determine the specific heat of a metal. You'll heat the metal up, generally to about 100 degrees. You'll put it into a calorimeter, measure the temperature change of the water in the calorimeter. You'll have the mass of the water in the calorimeter. You'll have the mass of the metal. You'll have the temperature change of both the metal and the water, and you can use this formula here to calculate the specific heat capacity, CPM, of the metal.